Alright, next example. A glass with a mass of 0.025 kilograms is dropped and hits the floor with a speed of 5 meters per second. What was the height of the glass's center of mass when it was dropped? Okay, so why would this be an energy problem if you were dealing with it on a test with a whole bunch of different types of problems? Well, I notice a couple things. Whenever I have a mass and a height, in this case I'm asked for the height, my brain thinks potential energy, gravitational potential energy. So you might want to get your brain in the habit of that. If you see mass and height, your brain should suggest to you gravitational potential energy. Might not actually be what you need to do in the end, but that's what your brain should suggest to you. And anytime I see the speed and a mass, my brain says kinetic energy. And so here, my brain says potential energy, and my brain says kinetic energy. So then my brain says, holy cow, conservation of energy. So something to think about there. This is a conservation of energy problem, and just like before, step 1 will be set up your initial and final conditions. And again, you don't even have to think about this. You just write initial, final, Ke plus Pe for the initial equals Ke plus Pe for the final. Next, we have to decide what the situation has at the beginning and at the end. So first, our glass is held at some height, as you can see in the picture here. So our glass is being held up. We need to know what kind or kinds of energy it has at the beginning. At the beginning, we're just holding the glass. It's not moving, so it can't have any kinetic energy. The glass does have a height, and the question specifically mentions the height. So here it does have a potential energy, and the type of potential energy it has is gravitational potential energy because it has a height. Not spring potential because there's no spring involved. At the end, the glass is moving, so right before it hits the floor, we could basically say its height is 0. And so that means it has no gravitational potential energy. There's also no spring in this problem, so it has no spring potential energy. So all it has at the end is kinetic energy, 1/2 m v squared. And we're asked to find h, the height. So we want to know the height. So we're going to solve for height. First of all, I could divide by mass, trying to get height by itself. And if I divide by mass here, the two masses on each side will just cancel. Then I need to divide by gravity on both sides. And I'm left with height equals 1/2 v squared over g, which could be written v squared over 2g. But fractions tend to trip people up, and I don't want to scare anybody right now. I'll save that for Halloween. Solving for the height, I'll just plug in the numbers. 1/2 velocity, 5 meters per second, squared, divided by g, which is gravity, so let's say about 10 newtons per kilogram. At this point, it would probably have been more helpful or easier to see the answer if I went ahead and put that 2 on the bottom, because then the bottom would just be 20, and 5 squared is 25. So I have 25 over 20. And if I divide 25 by 20, I get 1.25 meters. What would actually really be helpful, since based on today's quiz, I really want you to know units. Why don't you take the units in this problem, meters per second, which are both squared, and newtons per kilogram, and convince yourself that this problem does come out to be meters, so that it is dimensionally consistent, just like I had you confirm the second day of class for a bunch of things. See if the height, given the units in this problem, does come out to be meters. Check me on that. But there we go. Final answer, and that's how you use conservation of energy. Remember, conservation of energy can be used in a lot of different types of problems. So this could have been a kinematics problem. You could have said, oh, so if it ends with 5 meters per second, why don't I use gravity and the equation v squared equals v naught squared plus at, and then find its height using something else, to find the time. So basically what I'm saying, this could have been solved as a kinematics problem. Instead, we solved it as a energy conservation problem. So knowing how to do conservation of mechanical energy can get you out of a lot of trouble spots on both real life situations in physics. So if you need to figure out something real fast, conservation of energy is a good way to do it. Or on the AP exam, if you're like, I think this is kinematics, but it looks kind of like I could do it with conservation of energy. And if you can do it with conservation of energy, do it. You'll get the same answer. Reality is nice and consistent that way. Physics actually describes what happens in the real life. It's not made up, oh, you'll get one answer if you do it this way, and then another one if you do it this way. Because physics describes real life, you'll get the same answer either way. Anyway, that's all. Rewatch anything you need to, and hopefully the questions that I inserted tonight were helpful. Let me know in the meta notes. See you tomorrow.